Hi guys, today we are starting the other part of 9.4 that we usually include in the assessment that you took yesterday, but with all the AP tests going on, we decided to hold off on that. So here we are. So mathematical induction, this is a way to prove statements. So it's a type of proof that I don't think you've seen before, but we're going to go through two examples. And it is, yes, when you're doing mathematical induction that you follow the exact steps that I'm showing you. It's not just some crazy thing that I made up. Even though I did make up a proof, this is not it. All right, so here we go. So for mathematical induction, you let P sub n be a statement involving the positive integer n. And so there are two things, 1 and 2 here, that we're going to show, and we'll go through for each proof. Step 1, P sub 1 is true, and anytime P sub k is true, P sub k plus 1 is also true for every positive integer k. Then P sub n must be true for all positive integers n. Mathematical induction is kind of like a domino effect, and maybe after we go through one example I'll show that to you a little bit better, or it might be more clear to you. So we're only doing two examples, so maybe you can bear with me through both of them. So for both of these, you're using mathematical induction to prove the statement. I'm trying to get a different color pen. Ugh. And my phone's battery is dying, so I am plugged into the wall here. All right, so here we go. All right, so here's the statement, and you would be given a statement to prove, and here it is. So this is just number one, not this number one, but number one example. So S sub n is equal to 1 plus 2 plus 3 plus dot 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 plus n, which equals n times the quantity of n plus 1 divided by 2. Hey, does this look like something that we've done in the previous days? Yeah, it's the summation of just I, from I is 1 to n. I don't know if that looks familiar, but I hope it does. So we're going to prove it and derive it for you. Okay, so up above you see that number 1, and so just for your own information, this is called the base case. I always just say just the first step. So for the base case, we have to look at P sub 1. So basically for n is 1. Okay, so we say something to the effect of this. When n equals 1, the formula is valid because it's a lot of writing, I'm sorry. Okay, so S sub 1, so I put 1 in for n because n equals 1, this is your base case. Okay, well, what is S sub 1? S sub 1 is just 1. Okay, and now I have to verify, well, do I actually get 1 in the equation way over here on the right? Well, that's 1 times 1 plus 1 is 2 divided by 2, which is 1. So what I have shown there in that base case in step 1, you are showing that P sub 1 is true. Okay, so that's step 1. So now step 2 is called the inductive case. Okay, so again, it's a little bit wordy. You can shorthand it where you want. Okay, so let me see how we can shorten this a little bit. All right, so we are going to assume S sub k is equal to, and I'm going to put k into my equation that I was given here. So k times quantity k plus 1 divided by 2. So we are saying right now in our proof that we are assuming this. Okay, so we're assuming that S sub k equals that fraction there, and so we must show S sub k plus 1 equals k plus 1 substituted into here for n. So I'm taking where there's an n, and I'm writing k plus 1. So I'm going to leave it like this. I know that seems crazy, but sometimes it helps us to see what we're doing in our proof is true. Okay, so in the inductive case, we're assuming S sub k is true, and so therefore we must show that the next term, S sub k plus 1, the sum of the next term k plus 1 items is true using that equation. Okay, so since we are assuming that this is true, we can use that in the proof. So here we go. This is the heart of it all. Here we are. So I'm going to start out with S sub k plus 1. Why? Because I'm trying to get to this. I'm trying to show that S sub k plus 1 equals that. So I have S sub k plus 1. Well, that would be equal to S sub k, the sum of the first k terms, plus the A sub k plus 1th term. So I'm just breaking up, how can I get the sum of the k plus 1 terms? I can take the sum of the first k terms and then add on that last k plus 1 term. Okay, so because I assumed S sub k was true, I now can use this piece in my equation. So by substitution, I have k times k plus 1 over 2. And then what is the A sub k plus 1 term? Well, that's just this is the first term, the second term, the third term, the nth term. So A sub k plus 1 is just k plus 1. All right. So now it's just a bunch of arithmetic. So we have basically two fractions that we need to combine together here. So I would have k times k plus 1 plus 2 times k plus 1 all over 2. So you might be like, where are we trying to get to? Well, we're trying to get to here, remember. We want to show that it actually equals this here. So you could distribute, and I'm not saying my way is the only way to do it, like I always say, but what I see here is that I have two terms that both have a k plus 1. So I'm going to factor that out. And you'd be left with k plus 2 all over 2. So look, I have a k plus 1, k plus 1. I have a 2, and I have a 2. Well, hey, geez Louise, k plus 2, isn't that quantity k plus 1 plus 1? That is it. I mean, you could take that one more step and you're like, that's kind of weird, undo it. And just show that those actually are the same. So you did it. You really did it right here. You just had to realize, oh, wow, I actually have what I needed. And so to end this, we say, therefore, by mathematical induction, I just say math induction, the formula is true, is valid for all integers n greater than or equal to 1. So what just happened here, okay, is this domino effect. We proved that the base case was valid. Then we took some kth term, okay, and we said that if the formula holds for this particular number k, then it also must hold for the next number k plus 1. This is technically a conditional statement. Again, what I just said is, if this formula holds for a particular number k, then it must hold for the next number k plus 1, which is a conditional statement. All right? When we have finished step number 2, we haven't actually proven that it holds for any particular number. We're just saying that if S sub k is true, then the next number must be true as well. People always kind of have a hard time grasping this. So another way to think about it is, if I'm reading my notes, which I will take pictures of and post because some people like to read instead of listen. But so if the result happens to hold for some k, so that's right here, then it would necessarily have to also hold for k plus 1. But we're not really saying anything about whether it actually holds for k or not. We're not saying anything about that in the inductive step. We are just assuming that that happens. So this type of proof, people can usually get the pattern down, but it's kind of strange. how it is the domino effect. Remember, it's a domino effect. So the two parts of the proof, 1 and 2, all right, immediately tell us that the formula is valid for n equals 2. And so with step number 2 in the proof, that tells us the formula is valid for n equals 3. And then it tells us it's valid for n equals 4, and so on and so on and so on. Might not be your favorite. Okay, the other one I'm going to look at with you is this one right here, number 2. So again, we're using mathematical induction to prove. I need to reposition my sitting here. Okay, S sub n equals 1 cubed plus 2 cubed plus 3 cubed plus dot 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 n cubed equals n squared times quantity n plus 1 squared all over 4. Remember, this is the equation for the summation when you have I cubed. All right, so just as before, we have our base case. Okay, and so I'll try to use the same exact wording I used over here when n equals 1. Okay. All right, so when n equals 1, the formula, doing great, is valid because S sub 1 equals, well, what's, when I put 1 in, it's 1 cubed, which is equal to, okay, now I have to put 1 in over here. This thing would focus, that would just, help me a lot. 1 squared times 1 plus 1 squared is 2 squared over 4. Those cross out, they are the same. Okay. Making sure I should have done these on 2 separate pieces of paper. I'm just trying to stay consistent. Okay. So now we have the inductive case. Step 2. All right. So we will assume S sub k. Okay, so in that case, that's going to be k squared times quantity k plus 1 squared all over 4. Again, I'm trying to use the same words. We must show, okay, comma, we must show that S sub k plus 1 equals, so again, you're going to put k plus 1 where there's an n, so quantity k plus 1 squared times, I am going to keep the k plus 1 in parentheses, k plus 1 all squared divided by 4 is true. Alright, so here we go. So we're starting out with S sub k plus 1, and so again, S sub k plus 1, we can think of that as S sub k plus A sub k plus 1. Alright, so S sub k, using our equation, we're assuming that's true, so that's going to be k squared times the quantity k plus 1 squared all over 4 plus your A sub k plus 1 term, which is going to be, so that's the first term, the second term, the third term, we're cubing it, so the A sub k plus 1 term is going to be k plus 1 cubed. Alright, so again, there are a lot of ways you could go about doing the algebra and the arithmetic here. Some people might choose to FOIL things out. I don't know if that's really the most direct way, but it could. But so looking at these two terms here, what I notice is that they have a quantity k plus 1 squared in common. So I'm going to factor that out. Also, there's a hint here that I need this. So this is always what you're looking to get to. So I'm going to factor out a k plus 1 squared. So inside here, that's going to leave me with k squared over 4 plus quantity k plus 1. Okay, so this is looking good. We have a 4, we have a k plus 1 quantity squared. So now inside that bracket, I'm going to get a common denominator. And I hope with me you can make, let's see, we got the 4. You can make the leap with me to see that this would be k squared plus, if I multiplied this by 4, that would be 4k plus 4 all over 4. So again, that's just getting a common denominator and then distributing the 4 in. Okay, so these are two technically fractions, so I can bring that k plus 1 squared in the numerator. Now, remember, I'm trying to get, this is really k plus 2 quantity squared. And what's k plus 2 quantity squared? Oh, that's k squared plus 4k plus 4. So really this is k plus 2 quantity squared. And then again, just to show that, I'm going to rewrite this as quantity k plus 1 plus 1. Oops, I forgot my squared. Divided by 4, which is what we wanted to show. So I would end it by saying, therefore, by mathematical induction, what am I going to say? Well, I guess we could say, I feel like I'm trying to cut down on what you need to write here. The formula is valid for all integers n greater than or equal to 1. Oh my god, I forgot my box. Should have done it on the other side. I gotta have the box. So we realize that this takes some time, and we won't overwhelm you with the amount that we are doing, but we're going to work on this today and also tomorrow.